Welcome, science enthusiasts. Today we dive into the fascinating world of nuclear reactors. These technological marvels harness immense energy stored in atomic nuclei through a process known as fission. The result? Heat, which is then converted into electricity. In fact, nuclear reactors play a significant role in providing carbon-free electricity. In the United States alone, over 20% of total electricity and more than 50% of carbon-free electricity comes from these powerhouses. So what exactly happens inside these reactors that makes them so vital? Let's delve deeper. At the heart of every nuclear reactor is the process of nuclear fission. So what is nuclear fission? It's a process where the nucleus of an atom splits into two smaller nuclei, along with a few neutrons. This process releases a significant amount of energy, and it's this energy that we harness in a nuclear reactor. Now, you might be wondering, which atoms are we talking about here? Well, the most common atom used in nuclear reactors is uranium-235, a specific isotope of uranium. An isotope is simply a variant of a chemical element that differs in neutron number. Uranium-235 is particularly suitable because it can easily be split when struck by a neutron. Let's dive a bit deeper into the process. When a neutron strikes the nucleus of a uranium-235 atom, the nucleus becomes unstable and splits, releasing energy in the form of heat. But that's not all. The split also releases more neutrons, which then go on to strike other uranium-235 atoms, causing them to split and release more energy. This creates a chain reaction, and it's this chain reaction that keeps the process of nuclear fission going. It's important to note here that this process is highly controlled in a nuclear reactor. The reactor is designed to ensure that the chain reaction does not get out of hand. Control rods, made of materials that absorb neutrons, are used to regulate the rate of the chain reaction. So, to wrap it up, nuclear fission is a process where the nucleus of an atom, usually uranium-235, splits under the impact of a neutron. This split releases energy in the form of heat and additional neutrons that sustain the chain reaction. The energy released from this process is immense, and it's this energy that is harnessed in a nuclear reactor. This energy release is what makes nuclear reactors such power producers. But how is this energy transformed into electricity? Let's find out. The energy produced in a nuclear reactor is not directly usable. It needs to be converted into a form we can use, electricity. But how does this conversion take place, you ask? Well, let's dive right in. In a nuclear reactor, the heat generated from nuclear fission, which we discussed in the previous scene, is incredibly intense. This heat is not wasted. Instead, it is used to heat water. The water in the reactor becomes so hot that it turns into steam. Now, this isn't your everyday steam. We're talking about steam that's under tremendous pressure. This high-pressure steam is then directed towards a turbine. A turbine, in simple terms, is a machine that converts the energy in moving fluid into mechanical energy. In this case, the moving fluid is our high-pressure steam. As the steam rushes past the blades of the turbine, it causes the blades to spin. The spinning of the turbine blades is connected to a generator. Now, the generator is where the magic happens. It's where the mechanical energy from the spinning turbine is converted into electrical energy. How? Well, inside the generator there's a magnet and a coil of wire. As the magnet spins within the coil, it creates a flow of electrons. This flow of electrons is what we commonly refer to as electricity. The steam, after doing its job of spinning the turbine, is cooled down and condensed back into water in a component called the condenser. This water is then recycled back into the system to be heated again by the reactor, and the entire process repeats. However, it's important to note that the process we've just described is a simplified version. In reality, the systems in place to ensure the safe and efficient conversion of heat to electricity in a nuclear power plant are complex and numerous. So, we now have electricity thanks to the incredible processes occurring inside a nuclear reactor. But are all reactors the same? Not quite. There is a variety of nuclear reactor designs, each with its unique characteristics. Let's delve into some of these designs and see how they harness the immense power of the atom. Firstly, we have light water reactors, or LWRs. These are the most common type of nuclear reactor, and they use ordinary water, hence the name light, as both a coolant and a neutron moderator. This dual role of water is crucial. It not only helps control the nuclear reaction, but also carries away the heat produced during the reaction, which is then converted into electricity. While LWRs are the most prevalent, there are two main variants within this category: the pressurized water reactor and the boiling water reactor. In a pressurized water reactor, the water in the reactor core is kept under high pressure, preventing it from boiling. The heat generated in the reactor core is transferred to a secondary coolant loop, where it turns to steam and spins a turbine to generate electricity. On the other hand, in a boiling water reactor, the water is allowed to boil directly in the reactor core, and the resulting steam is used to drive a turbine. Next, let's move on to pressurized heavy water reactors, or PHWRs. Unlike LWRs, PHWRs use heavy water as a moderator. Heavy water, which contains a higher proportion of the hydrogen isotope deuterium, is a more effective moderator and allows for the use of natural, unenriched uranium as fuel. This is a significant advantage, as the enrichment of uranium is a costly process. Finally, we have gas-cooled reactors, or GCRs. In these reactors, the coolant is a gas, typically carbon dioxide instead of water. The gas absorbs the heat produced in the reactor core and carries it away to generate electricity. One key advantage of GCRs is that they can operate at higher temperatures than water-cooled reactors, potentially increasing the efficiency of electricity generation. Each of these reactor designs has its strengths and unique characteristics, reflecting the diverse ways in which we can harness nuclear energy. It's like having different types of engines for different types of cars, each one purpose-built for its specific task. As we see, there's more than one way to harness the power of the atom. But what about the future? Are there new designs on the horizon? As our energy needs evolve, so too does the technology to meet them. Enter advanced nuclear reactors. These innovative designs are the next generation of nuclear power, promising to deliver cleaner, safer, and more efficient energy. The most notable among them are fast reactors. Unlike traditional reactors that use slow neutrons to sustain the nuclear chain reaction, fast reactors use high-energy or fast neutrons. This key difference increases the efficiency of the nuclear reaction and reduces the amount of radioactive waste produced. Fast reactors are also capable of consuming nuclear waste from other reactors, transforming it into fuel. This nuclear recycling could significantly extend our nuclear fuel supply and reduce the challenges associated with waste disposal. Another important development in advanced nuclear reactors is the use of alternative coolants. Traditional reactors often use water as a coolant, but these advanced designs may use liquid metals, gases, or even molten salts. These alternatives can operate at higher temperatures without the high pressures associated with water-cooled reactors, improving efficiency and safety. And let's not forget about the small modular reactors, or SMRs. These compact designs can be mass-produced and shipped to sites for assembly, potentially reducing construction costs and deployment times. They also offer flexible power output and can be used in remote locations where larger reactors wouldn't be feasible. However, these advanced reactors are not without their challenges. High development costs, regulatory hurdles, and public perception issues are among the obstacles that must be overcome. But with continued research and innovation, these reactors could play a crucial role in meeting our future energy needs. These advanced reactors could potentially revolutionize how we generate electricity. But what does this mean for our future? Nuclear power is not just a part of our present, but also our future. As we move forward into the next decades, the importance of nuclear power in our energy landscape is set to increase dramatically. Advanced nuclear reactors are at the forefront of this evolution, promising to deliver more efficient and sustainable ways to generate electricity. While we've come to appreciate the substantial contribution of nuclear power in providing carbon-free electricity, accounting for over 20% of total electricity and over 50% of carbon-free electricity in the United States alone, we're beginning to understand its potential in shaping the future of energy worldwide. Advanced nuclear reactors, including fast reactors, are being developed to enhance efficiency and sustainability in nuclear power generation. These reactors promise to harness nuclear energy in a way that's more efficient, safer, and more sustainable than ever before. They also offer the potential to reduce the amount of nuclear waste produced, making them a more environmentally friendly option. But it's not just about efficiency and sustainability. Advanced nuclear reactors also offer the potential to help us meet the growing demand for electricity worldwide. As our need for electricity continues to grow, these advanced reactors will play a crucial role in ensuring we can meet this demand while also reducing our carbon emissions. Nuclear power through advanced nuclear reactors is poised to continue playing a significant role in our energy future. It's a future where we can enjoy the benefits of electricity without contributing to climate change. A future where we can power our homes, our businesses, and our lives in a way that's sustainable and responsible. Nuclear reactors, old and new, will continue to be a crucial part of our energy landscape. Nuclear reactors, a marvel of science, are more than just power generators. They represent the epitome of human ingenuity and technological prowess. The energy they produce is not simply the result of fuel combustion, but rather the outcome of a much more complex and fascinating process, nuclear fission. This process, which involves the splitting of atomic nuclei, releases a tremendous amount of heat. But what makes nuclear reactors truly ingenious is their ability to convert this heat into electricity. This conversion, carried out by intricate systems within the reactor, is fundamental to our modern way of life, powering everything from homes to industries. And let's not forget the diversity within the world of nuclear reactors. From light water reactors to pressurized heavy water reactors and gas-cooled reactors, each design brings its own set of advantages and challenges. But the quest for innovation doesn't stop there. The future holds promise for advanced nuclear reactors, including fast reactors, that aim to enhance efficiency and sustainability in nuclear power generation. The role of nuclear power in our future cannot be overstated. As we grapple with the challenges of climate change and the need for carbon-free energy sources, nuclear power stands as a beacon of hope. Thank you for joining us on this journey through nuclear reactors. Please subscribe for more exciting science videos. Until next time, keep exploring.